Hi guys, here's Dr. Diaz. And before we start with exponential growth and decay, remember I'm trying to set every Wednesday office hours from 11 to 11:50. So I always will have the Google Meet on, and I will send an invite email to all of you in case you have questions or you want to talk about the test or something. Well, that's the time. It's like office hours. Okay, so feel free to come those times because it's the same time we should have the class. If you have any questions, you can come those times. But if you cannot make it, you can email me any other time. Okay, but that's to let you know that we will have office hours online live, I should say, and I'm available to help you guys. So let's go here with exponential growth and exponential decay. Exponential growth and decay model. Look here. If we go to the growth, it says the mathematical model for exponential growth is given by this equation. Okay, and the exponential decay, the mathematical model for the exponential decay is given by this equation, which actually they look the same, and they are the same. The difference is, look at the graph. Exponential growth, this one looks is growing, while exponential decay looks what? Is decreasing, right? You're decreasing. Now, sorry. What is this equation about? Look here. Well, it's first it's exponential equation. We have here A naught, which is the initial amount. A is the final amount after a certain time t, because this variable here is t. And k here is what is known as the growth rate or the decay rate. In the case it's decay, right? Growth rate is always going to be bigger than 0. Decay is going to be smaller than 0, right? And sort of the problem is what you'll be doing is, for example, the one that you have on the review, you basically will be doing solving here for t because you want to know the time that thing it took to decay from, I think it was 200 pounds to 54. Yeah, that's the one from the review. And sometimes you can use it for a study, let's say population growth. Like this one in particular is used, the exponential growth is used for studying population growth, right? Like the population in a certain country, how it grow through years and stuff like that. Or in our case, the pandemic, the coronavirus, we know, well, the amount of people getting infected is growing. It's actually exponential growth. And what we wish it happened later after the curve is flattened is that everything goes like this one, decaying, right? So everything that virus thing disappear and we get back to normal. But be careful because we hope to get back to normal. But I think that virus is going to be somewhere around there waiting us for the fall. The thing is, we're going to work with these problems, solving for the constant k or for a time t in order to know, the time it took to decay or the time it took from growth from a certain number to another number. So let's do an example. Okay, this example is actually the one from the PowerPoint. It says that in 2000, the population of Palestinians in the West Bank, Gaza Strip, East Jerusalem was approximately 3.2 million. And by 2050, it is projected to grow to 12 million. Use exponential growth model, in which t is the number of years after 2000, to find the exponential growth function that model this data. And then b says which year the Palestinians is going to be 9 million. So first, we need to find k. Here's the equation that we have. Now what we're going to do is let's put it this way, kt is equal to natural log of a divided by a naught. And since we're solving for k, then k is equal to natural log of a divided by a naught divided by t. So substituting the numbers here, we get k is equal to what? Natural log. Instead of using the 12 millions and the 3 millions, let's use, the final amount is 12. Let's put 12 instead of 12 millions divided by 3.2 because both are millions. Let's say the millions and millions cancel. Divided, or it will be 10 to the 6, divided by t, which is 50. And if you do this, the answer is going to be, oops, that becomes too big, 0.026. This is approximately 0.026. Okay, so now we have the constant k, right? Great. K is equal to 0.026. This is the constant rate, the rate at which the population grows, you can say, per year. Now, If you remember, there's another question here. I'm going to move that question in a second. The second question is, in which year would the Palestinian population would be 9 millions? Okay, so now they're looking for t. And if you remember a moment ago, look at this equation that we have here. This equation has t. We solved this one for k. Well, before we solved for k, we got kt is equal to natural log of a divided by a naught. Now that we have k, and k is a constant, for this problem in particular is going to be always 0.026, we solve now here for t. And solving this for t, we will get something like this. T is equal to natural log of a divided by a naught times k. The same equation we got a moment ago with t, but now we're interchanging t and k. And this is going to be natural log of, okay, the final amount is not 12,000, now it's 9, divided by 3.2, which is always the initial, divided by 0.026. Why 9? Because the problem is asking you what will be the year in which the population is going to be 9 million, right? We already know that in 12 million is going to be in 2050, and we know that in 2000 is 3.2 millions. So by using our logic, we know that that amount, that year has to be between 2000 and 2050. So let's use it. Let's put this in here, and if we do this calculation, we're going to get something up. I was saying something approximately to 40, 39 point something, 40. So it's 40 years after 2000. So in which year the population of Palestine in East Jerusalem is going to reach 9 millions? In the year 2000 plus 40 in the year 2040. And does this make sense? Now we'll say yeah, because if you remember, in the year 2000 the population was like 3.2 millions, right? And then we calculated a moment ago that in the year 2050, we didn't calculate this, we know that the population it was given is going to be 12 millions. So somewhere in between is going to be what? 9 millions. And the point is, does this make sense? And the answer is yes, it makes sense. Okay guys, I hope this helped a little bit. It's a similar approach you're going to use for that problem on the PowerPoint, on the review. And the equation you're going to be using is actually this one. This one. Because you're looking for time of decay. Now be careful with this equation, because in that problem you will see that the final amount is actually smaller than the initial amount, and the value of a k is negative. It's like negative 0.0077. Hey, don't worry about that. We know times is positive, but when you do the natural log of a number smaller divided by bigger, it's going to give you a negative number, and this negative number and this negative number will cancel out. This is for that problem on the review. Okay, hope this helped a little bit. If not, you try to contact me and send an email, and you can bother me anytime. Okay, take care guys.